For most of Earth's history, there was no oxygen in the air. Not a trace. Not a fraction. The sky above the ancient ocean was a toxic mixture of methane, nitrogen, carbon dioxide, and hydrogen sulfide. A human placed on that shore would lose consciousness within seconds and be dead within minutes. Not from cold or heat. Simply from the absence of the one gas that every complex life form on Earth now depends on absolutely. And yet, something was about to change that. Something microscopic. Something that had no brain, no eyes, no intention. A single-celled organism so small that 1,000,000 of them could fit on the head of a pin. An organism that had been quietly perfecting a chemical trick for hundreds of millions of years. And when it finally deployed that trick at global scale, it triggered the most catastrophic and the most creative event in the entire history of life on this planet. This is the story of the Great Oxidation Event. The story of how cyanobacteria poisoned the world. And in doing so, made everything alive today possible. To understand what happened, we first need to understand the ocean those bacteria lived in. The Archean Ocean was nothing like the water we know today. It was warm, somewhere between 40 and 80 degrees Celsius in its shallowest zones. It was acidic, rich with dissolved iron, manganese, and sulfur compounds leached from volcanic rock. And it was completely without oxygen. Every drop of that ancient water was what chemists call anoxic. Oxygen-free, from the surface to the deepest trench. In that ocean, life had already been running for perhaps 1,000,000,000 years. The first organisms were simple prokaryotes. Cells with no nucleus, no mitochondria, no complex internal machinery. They lived by consuming the chemical energy available around them. Hydrogen sulfide from volcanic vents. Ferrous iron dissolved in the water. Simple carbon compounds. They were chemotrophs, deriving energy from chemistry rather than light. For hundreds of millions of years, this worked. The ocean teemed with microbial life, all of it invisible to any eye, all of it running on the chemical gifts of a volcanically active planet. And then somewhere between 3.5 and 2.5 billion years ago, something extraordinary happened in the evolutionary history of one particular lineage of bacteria. They learned to use sunlight. Not just sunlight. That trick had been attempted before by earlier photosynthetic bacteria using hydrogen sulfide as an electron donor, a process that produced no oxygen and left no lasting chemical mark on the environment. What this new lineage developed was different. Fundamentally, violently different. They learned to split water. Using the energy of sunlight captured by a molecule called chlorophyll, these bacteria could break the chemical bond between the hydrogen and the oxygen in a water molecule. They used the hydrogen to build sugars for energy. And they released the oxygen as a waste product, a byproduct of a reaction they had no interest in and no use for. These organisms were the cyanobacteria. And for hundreds of millions of years, even after they evolved this capability, their impact on the atmosphere was limited. The ocean itself acted as a massive chemical buffer. All that dissolved iron in the ancient seawater reacted eagerly with any oxygen that was released. Iron plus oxygen produces iron oxide. Risht. The oxygen was captured, neutralized, and deposited on the seafloor as a layer of rust-red sediment before it could ever reach the atmosphere. We can see this chemistry today in exposed rock. The great banded iron formations, those alternating stripes of red iron oxide and pale silica that streak through the geology of South Africa, Canada, Australia, and Brazil, are the geological fingerprint of this process. Hundreds of millions of years of cyanobacterial oxygen production, caught and neutralized by the chemistry of the ancient ocean, layer by layer, deposited on the seafloor like rings in a tree. But the ocean's capacity to absorb oxygen was not unlimited. The iron supply, enormous as it was finite. As the cyanobacteria multiplied across the shallow sunlit shells of the Archean Ocean, as they built their stromatolite reef communities in coastal waters all around the young continents, the rate of oxygen production slowly, relentlessly, began to exceed the rate at which the ocean could neutralize it. Around 2.4 billion years ago, the chemical balance tipped. For the first time in Earth's history, oxygen began to accumulate in the atmosphere. Not a great flood of it, not instantly, but measurably, detectably for the first time, free oxygen gas appeared in the air above the ocean surface. The geological record captures this moment with striking precision. Above the banded iron formations, the iron-rich sediments stop. Below a certain horizon, the chemistry of ancient soils preserved in rock shows the reducing conditions of an oxygen-free atmosphere. Above that same horizon, the chemistry changes completely. oxidized compounds, rust-colored weathering profiles, the unmistakable chemical signature of an atmosphere that now contained oxygen. Geologists call this boundary the Great Oxidation Event. And for most of the organisms alive at that moment, it was a catastrophe of almost unimaginable proportions. Because oxygen, while essential to us, is a profoundly reactive and dangerous gas. To the anaerobic bacteria that dominated Earth at that time, organisms that had evolved over billions of years in a world without oxygen, free oxygen was not a resource. It was a poison, a deeply corrosive, chemically violent toxin that attacked their cellular machinery and killed them. For the vast majority of species alive at 2.4 billion years ago, the Great Oxidation Event was a mass extinction. The greatest mass extinction in the history of life on Earth, dwarfing every event that followed, including the asteroid that killed the dinosaurs. Perhaps 99% of all species alive at that time were wiped out. Not by an asteroid, not by volcanic eruption, not by any external catastrophe. By the metabolic waste product of a single lineage of photosynthetic bacteria that had become globally dominant and changed the rules of chemistry for the entire planet. The cyanobacteria had poisoned their world. And yet what seems like the end was in fact the beginning of something far more extraordinary. Because in the face of this chemical catastrophe, life did not simply die. It adapted. And in adapting, it made every complex organism on Earth possible. Some anaerobic bacteria retreated. They found refuge in environments that remained oxygen-free. Deep sediments, the interiors of other organisms, anoxic pockets in the ocean and soil where oxygen never penetrated. Their descendants survive today in exactly those same refuges, billions of years later, unchanged in their fundamental chemistry. But other lineages found a different solution. Rather than hiding from oxygen, they learned to use it. Aerobic respiration, the process by which cells extract energy from oxygen, is roughly 18 times more efficient than the anaerobic alternatives that preceded it. 18 times more energy from the same amount of food. This enormous energetic advantage drove an evolutionary explosion. Organisms that could use oxygen could grow larger, move faster, build more complex structures, and invest more energy into reproduction and adaptation than anything that had come before. And then something even more remarkable happened. Approximately 1.5 billion years ago, one of these aerobic bacteria was engulfed by a larger cell. Not digested, not destroyed, but incorporated. The engulfed bacterium continued to function inside its host, providing energy through aerobic respiration. The host provided protection and nutrients. Over generations, the relationship became permanent. The engulfed bacterium slowly lost its independence, transferred most of its genes to the host nucleus, and became an organelle. We call it the mitochondrion. Every cell in your body contains hundreds to thousands of mitochondria. Every cell in every animal, every plant, every fungus on Earth. All of them descended from that single ancient event, that one moment when an anaerobic cell engulfed an aerobic bacterium, and instead of destroying it, built a partnership that would last for 1.5 billion years. The energy supply that the mitochondrion provided made complex multicellular life possible. It made the Cambrian explosion possible. It made muscles, nervous systems, and brains possible. It made you possible. All of it tracing back to the cyanobacteria. But the story of the Great Oxidation Event does not end with the rise of aerobic life. Because the appearance of oxygen in the atmosphere triggered another transformation, one that we can actually see in the rock record as a direct consequence of the rising oxygen levels, a transformation so severe that it very nearly ended everything that the cyanobacteria had set in motion. Methane. The early Archean atmosphere contained significant quantities of methane produced by the metabolic activity of those same ancient anaerobic bacteria. And methane is a powerful greenhouse gas. It was that methane, in the absence of oxygen that would have destroyed it, that kept the early Earth warm enough for liquid water to exist despite the fact that the young sun was 30% dimmer than it is today. When oxygen began accumulating in the atmosphere, it reacted with that methane. Methane plus oxygen produces carbon dioxide and water. Carbon dioxide is a far weaker greenhouse gas than methane. And as the oxygen levels rose and the methane was destroyed, the greenhouse effect collapsed. The planet entered the most severe glaciation in its history. Snowball Earth, a period geologists call the Huronian glaciation, lasting perhaps 300 million years, during which ice sheets extended all the way to the tropics, and the entire surface of the planet may have been locked under kilometers of ice and snow. Not everywhere. Not completely. The geological evidence remains debated in its details. But something catastrophic happened to Earth's climate as a direct consequence of the oxygen revolution, and the planet came closer to becoming a permanently frozen, lifeless ball of ice than at any point before or since. Life survived in hydrothermal vent systems beneath the ice, in pockets of liquid water kept open by geothermal heat, in sediments and deep ocean environments where enough warmth remained to sustain microbial communities. And the planet eventually warmed again as volcanic outgassing slowly rebuilt the carbon dioxide levels in the atmosphere and the ice retreated. When the Huronian glaciation ended, the world that emerged was fundamentally different from the one that had entered it. The atmosphere now contains several percent oxygen. Not yet the 21% of today, but enough to begin driving the next set of transformations. The ozone layer began to form, a shield of triatomic oxygen molecules in the upper atmosphere that filtered out the lethal ultraviolet radiation that had previously prevented life from colonizing the land surface. The ocean chemistry was transformed. Iron was now largely precipitated out of the water column. The ancient rust-red banded iron formations stopped forming. The shallow seas that had once been dark and iron-rich became progressively clearer and more chemically similar to modern seawater. And in those clearer, oxygen-containing oceans, complex eukaryotic life was diversifying. Cells with nuclei, cells with mitochondria, cells capable of merging and specializing in ways that anaerobic cells had never managed. By 1 billion years ago, the first true multicellular organisms were appearing. Not colonies of identical cells, but organisms with different cell types performing different functions. Division of labor, specialization. The beginnings of the body-plan principle that would eventually produce, after another 1 billion years of evolution, every animal on Earth. The cyanobacteria that triggered this entire cascade are still here. They live today in every ocean, every lake, every moist soil surface on Earth. They are the most numerous photosynthetic organisms on the planet. They still produce a significant fraction of the oxygen in every breath you take. They have been doing this without interruption for somewhere between 2 and 3 billion years, and they will almost certainly continue long after every complex organism alive today is gone. They did not intend to change the world. They had no intention at all. They were simply doing what evolution had equipped them to do. Capturing sunlight, splitting water, growing, dividing, spreading across every sunlit surface the planet offered them. And in doing so, they produced a poison that killed the world they lived in and built the foundation for a world of unimaginable complexity and beauty. Every breath you take is the legacy of that ancient, unintentional revolution. Every heartbeat is powered by mitochondria that trace their ancestry to a bacterial partnership born from crisis. Every living thing you have ever seen, every creature that has ever drawn breath, every plant that has ever turned toward the sunlight, every organism that has ever existed on this planet in the last 2 billion years owes its existence to the cyanobacteria, to the ones that poison the world, and in doing so made it.